creation stories of Pacific Islanders tell us the world was made from a volcano. Other origin myths say the world came from water. But contemporary science tells us that the world evolved from a Big Bang. And the outdated view that this marks an absolute beginning has been used by religious philosophers, most notably William Lane Craig, to revive an old argument for God known as the Kalam cosmological argument. In this film, we'll hear why this argument fails from the very cosmologists quoted by Kalam's supporters. And we'll also hear from leading philosophers of mathematics who will show why the concept of an infinite universe, now being proposed by many physicists, is perfectly coherent. And lastly, we'll see that if the universe did begin, it may not need a cause. The argument is often expressed like this: whatever begins to exist has a cause. The universe began to exist. Therefore, the universe has a cause, and that cause is taken to be God. Let's start at the beginning. Philosophers like Craig have argued that the past must be finite.
If the universe never began to exist, that means that the number of past events in the history of the universe is infinite. But mathematicians recognize that the existence of an actually infinite number of things leads to self-contradictions.
As we shall see, contemporary mathematicians do not think infinity is contradictory, although it's true that philosophers of the past were troubled by it. But even they did not banish the concept. For example, Aristotle distinguished between different types of infinity.
The distinction that he was drawing was between an infinity that's present all at once, all at some particular point in time, which is what he meant by an actual infinity, contrasted with an infinity that is spread out over time, which is what he called a potential infinity. So, for example, if space were infinitely big, that would be an example of an actual infinity because the whole of space is there at any given point in time. On the other hand, if you imagine a clock endlessly ticking, the ticks might go on forever, but if they did, that would be an example of a potential infinity.
But in the 19th century, Georg Cantor revolutionized the mathematics of the infinite.
What Cantor achieved was to treat infinity as a subject of mathematics itself.
It was a whole new branch of mathematics, and it was of breathtaking ingenuity, showed incredible craftsmanship and creativity on Cantor's part.
What Cantor showed was that an infinite set has a strange feature. We might call this the infinite property. That is, it can be put into a one-to-one correspondence with a subset of itself.
We can pair the even numbers up with all the numbers, all the counting numbers all together. So 2 gets matched with 1, 4 gets matched with 2, 6 gets matched with 3, 8 gets matched with 4, etc., etc.
So, for instance, you can show that there are just as many even numbers as there are counting numbers, when intuition should tell you that there be half as many.
Well, okay, so this just is counterintuitive, and it's counterintuitive because we're used to dealing with finite sets, and what we have to say in the case of finite sets just doesn't carry over to the case of infinite sets. But it doesn't follow that there's anything incoherent about what we say in the infinite case. It just follows that we have to start saying different things in the infinite case.
What you get from most mathematicians, I would say almost all mathematicians, is an uncritical acceptance of infinity in the sense of actual infinity. That's what they need for doing the kind of mathematics that they do.
So one of the first things that mathematicians come to appreciate is that infinite collections do have different properties from finite collections. Things that we absolutely take for granted in the finite case simply don't carry over to the infinite case. And if it's the finite case that is providing us with our basic intuitions, then that means that some of the results about infinite sets are going to be counterintuitive. But that's just what you would expect. Why should the finite and the infinite be the same? As long as we're prepared for these differences Again, the very worst that it will be is counterintuitive. It won't be contradictory, it won't be inconsistent.
So one way to bring out the difference between the finite and the infinite is to think about somebody counting. So imagine George is counting to 10 and he's got as far as 5. How many numbers has he got left to count? Oh, he's got 5 numbers left to count, 6, 7, 8, 9, 10. But now imagine George is going to count all of the numbers, every single counting number. And he's got up as far as 5. How many numbers has he got left to count? He's got infinitely many numbers still left to count. What about when he gets to 10? How many numbers has he got left to count? He's still got infinitely many numbers left to count. So his task isn't going down over time, but when he's counting a finite set, his task is going down over time.
One classic example that Craig has given to show infinity cannot exist is that of Hilbert's infinite hotel.
The mathematician David Hilbert illustrates the problem by imagining a hotel with an infinite number of rooms, all of which are occupied. There's not a single vacancy. Every room in the infinite hotel is full. Now suppose a new guest shows up and asks for a room. The manager says, "Sure, no problem," then moves the guest who was in room number 1 to room number 2, and the guest who was in room number 2 to room number 3, and so on to infinity. As a result of this shuffling, room number 1 becomes vacant, and the new guest happily checks in, even though all the rooms were already full, and nobody has checked out.